Onward we forge into the Aldol abyss. Oh no, it's not an abyss. It's not bad. So the Aldol, we're not going to start with the Aldol. I'm going to give you the key to the random reagents that I gave you at the end of the last mini lecture. So there they are. You can pause this if you want to write them down. But meanwhile, we will forge onward into the Aldol abyss. We're wrapping up chapter 18, believe it or not. But as I mentioned earlier, the Aldol's a pretty big deal. So we actually have a fair amount to cover in chapter 18, and I'm pretty certain that not all of this will be on the exam, but some of it will, so listen up. We've already been introduced to Aldol in class. It's the same old electrophile, the carbonyl of the aldehyde or ketone, but the new nucleophile is the enolate, as shown here. So, the Aldol can be catalyzed by acid or base. I'd say it's more typically catalyzed by base, as in this example. So we have pentanal and what appears to be a good base. So, what's going to happen here? Well, I know I have a base/nucleophile here, so I need to be thinking about what's going to happen over here. And as I mentioned in class, it makes perfect sense that you would add to the carbonyl carbon, and you'd think, well, there you go. That's what I got. And the problem with this is you can't go any further, because I can't protonate this under basic conditions. I can't kick it out. I can't make an acetal. So this is a reversible reaction, and eventually, instead of attacking at the carbonyl carbon, my base/nucleophile is bound to come to the alpha hydrogen. So I will put in my alpha hydrogens because line structure, of course, doesn't show them. Deprotonation gives me the enolate. And again, this is, of course, a reversible step. It's acid-base. But now I've made a carbon nucleophile, and the only carbon electrophile that's around is right here. This is going to be a reaction between the enolate of pentanal and pentanal itself. So, draw up another molecule of pentanal, and nucleophile, meet electrophile. Now, it's important to note that this too is a reversible step, and it's completely legitimate to be wondering, well, why wouldn't this go back the other way? I add that carbon here, so there's a hydrogen attached to it, a propyl group attached to it, and the aldehyde, the carbonyl carbon. Why should this stick? Well, in effect, it doesn't necessarily. It's easy for this to go back the other way. It's like the other reactions we've looked at in this chapter. We're going to have to do something to pull the equilibrium along to product. Well, one way we can pull the equilibrium along to product is to make a stable product. And, well, we're not going to protonate with water because we don't have any water present. We have our solvent methanol present. So, protonation gives me the aldol product. And I'm just going to redraw it slightly. and kind of color code it so it's clear that I have two 5-carbon pieces from my pentanal. So this is my pentanal electrophile, and this was my pentanal nucleophile. And here is my new carbon-carbon bond, and there's my aldol product. Now the actual aldol from aldehyde alcohol, the aldol product isn't super stable, but it's pretty easy to have dehydrate, in which case you lose water and end up with a super stable product. And I'm going to have to get my, I'm moving things around on you, but I'll color code them here again. So my orange enolate aldol is 1, oops, I want to go here. 1, 2, 3, 4, 5. And my yellow electrophile partner of the aldol is right here. 1. Having a little trouble here. 1, 2, 3, 4, 5. So I lost this hydroxyl group and that hydrogen as water to form that double bond right there and make this very stable conjugated product. So that's one way that we push the equilibrium forward to get the aldol product. When the aldehyde is both the nucleophile and the electrophile, in other words, it reacts with itself, that's called the self-aldol, and it's less complicated. So, as we just showed in the previous slide with the mechanism I went through, these are the two products of a typical aldol. Some real big screaming hints that you've made an aldol product here. First of all, every aldol has this 1,3 relationship between the aldehyde or carbonyl and the hydroxyl. So by 1,3 I'm simply pointing out that if this is carbon 1, this is carbon 2, this is carbon 3. There's a hydroxy group on carbon 3, a carbonyl on carbon 1. The other screaming bell and whistle for an aldol is, again, the alpha-beta unsaturated carbonyl. If you've got a target that has an alpha-beta unsaturated carbonyl, it can be made by an aldol. So, retrosynthetically speaking, the aldol opens up a world of possibilities because it makes new carbon-carbon bonds and pretty handy functionality. When I see this 1,3 relationship, what I'm going to do is think, oh yeah, okay, I could punch that pair of electrons back in here and kick that guy out as an enolate. Oh yeah, there's my aldehyde and there's my enolate. This plus this will give me this. You betcha. If I have an alpha-beta unsaturated carbonyl, well, it's not quite as obvious. But if you remember that the alpha-beta unsaturated species came from an aldol, well, then you can write up the aldol precursor, the non-dehydrated precursor, and that would of course be this guy with that 1, 2, 3 relationship. Once I've drawn this up, then again I play that game of pushing the lone pair from oxygen back down to make a carbonyl, That gives me the aldehyde, my electrophile, and the enolate nucleophile. Easy as pie. So, what should this remind you of? Our alcohol disconnection. We just went through this in great gory detail in the beginning of, gee whiz, chapter 17, where I showed you how anytime you have an alcohol, you can imagine this disconnection where you push the electrons from oxygen back in and you either kick out this as your nucleophile, or I can't use that guy, I'll use yellow, which you can't possibly see, this as a nucleophile, or this as your nucleophile. Well, now we're doing the same thing with the aldol. Push her in, push her out. What do we got? This aldehyde plus this enolate. Those two, put them together, this is what you got. So, synthesis will play a big role in understanding aldol chemistry. Aldol, screaming aldol. Alright, now, what about this crazy dehydration step? It's kind of fishy. It's kind of making you think, well, Carpenter is a big fat liar because this doesn't make any sense. So what's happening here? Well, what's happening here is that I have a base that is deprotonating here, and that's fine and dandy. I don't have any problem with that. You shouldn't have any problem with that, because after all, you're just making the enolate. There it is. A problem you should have is, why does it remove this hydrogen and not this hydrogen? Surely this is the more acidic hydrogen, and you'd be right. But keep in mind, first of all, that we are driven by results, and the result is, this is what we get. NMR proves it, IR proves it, we know this is the product. So how do I rationalize its formation? Well, I rationalize it by proposing the following mechanism. That this hydrogen is removed, I'm sure this one is removed at some point too, but all kinds of protons are coming off, and once this one is deprotonated, I basically have the conjugate base of my alpha hydrogen acid. This is the part you're not going to like. It's going to pop down here and kick out, oof, minus OH minus? What? I always told you that's a terrible leaving group, and you know what? It is a terrible leaving group. Trust me on that. It's a terrible leaving group. But this is such a stable system that is the driving force, the complete driving force for forming the dehydration product. So yes, you can kick out a lousy leaving group, but only if you're making a humongous thermodynamic sink that's driving you to a very stable product. So problem 18.25 will help you, well, I think help convince you that this isn't totally random magic. I hope. Alright, some other points to make about the aldol. It can be run under acid catalysis. Typically it's basic catalysis. And it works a lot better for aldehydes, but ketones can undergo the aldol reaction as well. The problem with ketones is sterics, that when you add to the the enolate to the ketone, there's a lot of banging around going on there, and so the equilibrium is not very favorable. Well, it does work though, so here's a nice example of an acid catalyzed aldol that forms in 71%. Let's quickly run through the mechanism. So, acid-base chemistry, acid-base always wins. We're under acidic conditions. So, protonate that carbonyl and get a more electrophilic carbonyl. And yes, it makes sense that the Cl- would attack here, and it won't get you anywhere. So that's a reversible reaction. Every once in a while, that Cl- will go ahead and make the enol. And once the enol is formed, I have my carbon nucleophile. So here's the enol, and I've regenerated my catalytic amount of HCl. The enol can react with another molecule of cyclohexanone, but of course, since we're under acidic conditions, that will already be protonated. So we will use the lone pair to push those electrons out, and the nucleophilic alpha carbon will react here at the electrophilic carbonyl to give me a new carbon-carbon bond. So I'm going to put my hydrogen in, and here I have made OH. Alright, so new bond between this guy and the carbonyl carbon. So there it is. And I think you can figure out how the product is formed from there. So there's another nice aldol for you. Again, I want to emphasize the fact that if you want to get a good yield, you can dehydrate your aldol product to get to the alpha-beta unsaturated conjugated system. That's not all that difficult. All it takes is a little heat, and that can take place under acidic or basic conditions, as we've already seen. Okay, now it gets real ugly real fast when you start mucking around with different aldehydes and ketones. So say for example I have this aromatic ketone and acetone, and I throw in base hoping to get a product. Well, to make it real straightforward, you're going to be able to have products where A reacts with itself, where B reacts with itself, where A is the enolate and B is the electrophile, and where B is the enolate and A is the electrophile. So your TLC is kind of going to look like this. Yuck. A messy, messy bunch of spots that kind of looks like a tire skid. So let's look at what A and B really would be. A and A, that would be the reaction of this enolate with another molecule of this ketone. So that's going to give me that product. Okay. B and B, well, here's B. There's the 1,3 relationship. There's molecule B. So I'll just kind of color code the electrophiles here. Looking ugly already. If A is the enolate and B is the electrophile, what do we get? We get that guy. So this is AB. And what if the table's turned? Then we have BA. So there are your 4 mixed aldol or crossed aldol products, and as you can see, nobody wants that. They're all pretty much equally favorable. What are you going to get? 25% yield at most of any one product. So pretty much this is a big giant junk pile down the sink waste. Of course, we're not really going to put anything down the sink, but you get my drift. So what can we do about this? There are ways around the mixed aldol mess. First off, the easiest way is to make sure that one of the two things you're trying to make can't be turned into an enolate. So for example, benzaldehyde plus propanal, that ought to work, because it doesn't matter how much base I throw in, there's no alpha hydrogens on this guy. So if I form the enolate on propanal, I should be able to fairly selectively make my aldol product. Now, you may ask, what about the self-aldol? It's not too hard to control if you're smart. Because if I add the propanal to a mixture of the base and benzaldehyde, so I'm dripping the propanal in slowly to the base and the benzaldehyde already in the flask. As soon as that propanal hits the base, it's going to be deprotonated. And what is it going to run into? Well, it's going to run into the benzaldehyde, because the rest of my propanal isn't in the flask. It's sitting up above in a pipette or a syringe or something. So you can control the self-aldol and minimize its formation. Another way you can control the mixed aldol problem is to just make sure that you make the enolate of one of the two partners first, and then combine the two. So, say for example, I wanted to make this aldol product. Now that's going to be a bit of a problem if I just throw everything together. Using my little retrosynthetic disconnection, I can see that I would want to add this enolate to this aldehyde. Well, major problems here, because of course I can form an enolate there as well. So why don't I keep that out of the picture and figure out a way that I can make this completely and stoichiometrically first. I can do that if I add a strong enough base. For example, lithium diisopropylamide. So lithium diisopropylamide can deprotonate this guy. My conjugate acid is diisopropylamine, and basically, no pun intended, that's a favorable equilibrium, because the enolate is comparable in stability. You might want to look up the pKa values. Comparable in stability to the lithium diisopropylamide. So I can add one equivalent of lithium diisopropylamide to this ketone, make sure everything has been deprotonated, I'm all the way to my enolate, and then I can drip in my aldehyde and get my desired product. So there are ways around this mess, and the aldol mess is something that takes well to a lot of drill. So we will be doing lots and lots of aldol problems in class. So remember to focus on mechanism, and that will help keep your eyes from crossing, and it'll also keep you from pulling your hair out, and probably minimize headaches at the same time. So see you in class.